First bad version. This one sneaks up on candidates. First bad version looks easy, but it tests whether you can turn a plain binary search into a boundary finder. FANG interviewers love it because getting the loop and the off by one details right under pressure is a real signal. Let's lock it in with basic, so your explanation and code are crisp and bulletproof. Solution walkthrough. Breakdown. We have versions 1 through n, and an API called isBadVersion of X that returns true if version X is bad. Once a version is bad, every later version is bad. We must return the first bad version's index. That's a classic monotonic pattern. FFF, FTTT, T. We're not searching for a value, we're finding the leftmost true. Assess. Linear scan is O of n, but the predicate is monotonic, so binary search gives us O of log n time and O of 1 space. The pitfalls are the termination condition and deciding which side to keep when mid is bad. If mid is bad, the first bad could be mid or somewhere to its left. If mid is good, the first bad must be to the right. Structure. We keep a closed interval from left to right, initialized to 1 and n. While left is less than right, we compute mid. If isBadVersion of mid is true, we shrink right by setting right equal to mid. Otherwise, we move left past mid by setting left equal to mid plus 1. When the loop ends, left equals right, and that index is the first bad version.
Let's try to implement it using solution 1. We start by defining a class called solution, which groups our method neatly inside it. This defines the function firstBadVersion, which takes in n, the total number of versions. Our goal is to find the first version where the product turned bad. We set 2 pointers. L starts at version 1, R starts at version n. This creates the full range we'll search through. We initialize bad to n. The worst case assumption is that the last version is the bad one. As we narrow things down, we'll keep updating this to the earliest bad version we find. We continue searching as long as the left pointer has not surpassed the right. Because we repeatedly cut the range in half, this loop runs in O of log n time. We calculate the midpoint of our current search range. This is the version we'll test next. Similar to checking the middle shelf to see where a problem starts. We call the provided function isBadVersion on the middle version. If this version is bad, it means the first bad version must be at mid or somewhere earlier. Because the midpoint is bad, we update our bad variable. This might be the earliest one. Then we shrink the search range to the left half, since earlier versions might also be bad. If mid is not a bad version, then the first bad version must be to the right. So we move the left pointer rightward to search the later versions. Once the search finishes, bad holds the earliest bad version we found, and that's what we return. And that's how this algorithm works. It first sets up a full search range, then uses binary search to repeatedly test midpoint versions and narrow down the earliest bad one. Efficient, simple, and elegant. Check. Let's walk through this test case for the first bad version problem, where we use a binary search style strategy to find the earliest version that fails. Input is n equals 5, bad equals 4. Here's what the input means. Versions are numbered 1 through 5. Version 4 is the first bad one. Any version after 4 is also bad. Any version before 4 is good. Our goal is to identify the very first version that is bad. Why the output is 4. Let's simulate the logic. First, we check the midpoint between 1 and 5. Mid equals 3. Version 3 is good, so the first bad version must be after version 3. The new search range is 4 to 5. Now mid equals 4. Version 4 is bad, so this might be the first bad version, but we must check if there is any earlier one. Next, the search range becomes 4 to 3, meaning the left side closes and the loop ends. That confirms 4 is the first bad version. So the algorithm locks onto. The output 4 matches the expected 4, confirming that the solution correctly identifies the first bad version in the sequence. Now let's try another implement approach using solution 2. We start by defining a class named solution, which is simply the container for our method. This sets up the main function firstBadVersion, which receives n, the total number of versions we need to check. Inside our main function, we define a recursive helper function. It takes 2 values, L, the left boundary, and R, the right boundary. This helper will perform the binary search through recursive calls. This is the base case. If the left boundary meets or passes the right boundary, it means we've narrowed the search down to a single version, the first bad one. When that happens, we return L, because it represents the earliest possible bad version. We compute the midpoint of the current search interval. Binary search always checks this midpoint first. The halfway point helps us decide which direction to search next. We call the provided API function is bad version of mid. If the midpoint version is bad, then the first bad version must be at or before this midpoint. So we recursively search the left half of the range, including mid itself, because it might be the earliest bad version. If mid is not bad, then the first bad version must be somewhere after mid. So we recursively search the right half of the range, starting just after the midpoint. To kick off the recursive binary search, we call our helper on the full range of versions, from 1 to n. And that's how this algorithm works. It first sets up a recursive helper to search between left and right bounds, then keeps having the range based on whether the midpoint is bad until it isolates the earliest version. Efficient, simple, and elegant. Check. Let's walk through this test case for the first bad version problem. It's the simplest scenario but a great sanity check. Input is n equals 1. Bad equals 1. Here's what this means. There is only one version, version 1. Version 1 is already marked as the first bad version. There are no earlier versions to compare against. Why the output is 1? Since the problem states that all versions before the first bad version are good. All versions from the first bad version onward are bad. And here we only have a single version that is bad. It must automatically be the first bad version, which is 1. No binary search is needed beyond checking that 1 value. The output 1 matches the expected 1, confirming the logic works even on the smallest possible input case.
Let's have a quick recap. Breakdown recap. So, wrapping it up, the first bad version problem isn't about finding a value, but identifying a boundary. We're given versions from 1 to n, and once one version is bad, all the ones after it are bad too. Our goal is to pinpoint the very first bad version, the exact point where good turns into bad. Assess recap. We compared our options and saw that a linear scan would work, but it's way too slow. The key insight is that this setup is monotonic, which means we can apply binary search. The trick is in how we move our pointers, deciding which half to keep and which to drop, while never losing sight of the possible boundary. Structure recap. The plan was simple but precise. Start with the full range from 1 to n. On each step, check the middle version. If it's bad, the first bad could still be to the left, so we keep mid in play. If it's good, we move right past mid. The loop ends when both pointers meet, and that meeting point is the answer. Implement recap. In the implementation, we used a clean binary search loop, updating our boundaries carefully. We avoided off-by-1 errors by keeping the logic tight. Bad means shrink the right boundary, good means move the left boundary forward. It's a perfect example of control and precision in algorithm design. Check recap. When we ran the tests, every case passed, whether the first bad version was early, late, or right at the start. The function consistently returned the correct index with O of log n time and O of 1 space, just as expected. The big takeaway? Boundary-style binary search is about discipline, not just finding something, but knowing exactly where a condition changes. Mastering this pattern builds the confidence and accuracy the top interviews are designed to test.